On how to make and analyze pedigrees. So, a pedigree is going to be something that displays individuals within a gene pool, meaning they're related. They have had sex, they have made babies, they have siblings, they have parents. And the pedigree displays two really important things within a family or a gene pool. The first is going to be generations, so generation 1, generation 2, generation 3, and also biological sex. And biological sex refers to, more specifically in humans, the combination of X and Y chromosomes that you have. It's only important in certain traits that are coded for on the X or Y chromosome. A lot of the traits that we deal with are called autosomal traits, which means they're not coded for by sex. If an individual in a pedigree is shaded in, it almost always means that they're afflicted with the trait or characteristic that we're looking for. Individuals that do not express the trait or might show a smaller degree of that trait are usually not shaded in. So white often means no expression. Dark means that the trait is expressed. And as I said, circles are going to be what we call biological females, and squares are going to be biological males. For simplicity, we're going to assume that all biological males are XY and all biological females are XX, but that is not the case. You can be XXY, XXX, X, etc. Biological sex is something that we often say is binary, and for the most part it is. But when we think about the chromosomes, the X and Y chromosomes that make up humans, it's not so simple. So the first type of pedigree that you can look for is known as autosomal dominant. And autosomal dominant means that the trait is expressed if you have a phenotype with at least one or more dominant alleles. So big A, or big A, little a. The reason why that you tend to see this is, or how you tend to see it is, it tends to be the most common or the most normalized version of a trait, and it often doesn't skip a generation. So generation 1 has it, generation 2 has it, generation 1 has it, generation 2 has it. Some individuals do not show this trait even though it's dominant because they are recessive, little a, little a, little a, little a, which means if you're a carrier for the trait, you can have children that don't have this trait. So these two individuals are probably big A, little a, big A, little a, big A something, little a, little a, little a, little a, so big A, little a, little a, little a. If these two individuals are little a, little a, and little a, little a, none of their individuals will show it. So if you're dominant, if you're a dominant pedigree, all of the children will show it, or none of the children will show it. Some dominant traits are not necessarily good. So, for example, versions of dwarfism are dominantly inherited traits, which means that if you have a stunted height or growth within, say, your legs or arms, that is the result of the dominant allele. And Huntington's disease, which is an autoimmune neurodegenerative disease, is also a dominant allele, which basically means if a parent has it, it can be almost always guaranteed to be in a child. So I want you, and I've already said this, so if you're watching the video, good for you. I want you to describe the likely genotypes for individuals 1, 2, 4, 6, 7 using A or little a. And the second question is, what is the probability if individual 5 marries a phenotypically recessive individual that they have individuals that display the recessive trait? So autosomal recessive is the opposite. Autosomal recessive, the individual, the phenotype that expresses the trait is little a, little a. This often means two things. A, you can have individuals have the trait when both parents don't have the trait, and or the trait can skip multiple generations. A lot of recessive traits are what we call genetic diseases or disorders. So cystic fibrosis and sickle cell anemia, which are two really common diseases in human populations, are both little recessive alleles. Albinism, or the lack of pigmentation, is also a recessive disease. Often carriers, which are heterozygous individuals, make enough of the formed protein that they appear to not have the trait, but they still have that recessive allele, which means that if two carriers have an individual that gets the recessive allele, those children will have that trait. So I want you to describe in this pedigree the genotypes of 1A, 2A, of 1B, of 3B, and of 4B, and of 1 and 2 of C. And then I want you to also describe whether or not 3B and 4B, their children, do or do not have the recessive allele. And then the last type of pedigree is X-linked recessive. An X-linked recessive is a trait in which if you have one or two versions of a recessive allele on your X chromosome, you express the trait. So that means that females that express the trait are little x, but males that are little xy have the trait because they only have one copy of the X chromosome. To know if a trait is X-linked, it means that often males have a higher rate of the phenotype being expressed. So a good example of this is color blindness. About 1 in every 100 females have a version of color blindness. Males are about 1 in every 6. And that is because the genes that code for being able to see color are coded on the X chromosome. Females have more options. They can be big X, little x, or little x, little x. Males are either dominant or recessive, and we say they're homozygous because they have that Y chromosome also. So I want you for this pedigree to describe the genotypes of 4, 6, 10, and 12. 4, 6, 10, and 12. And also to say whether or not it'd be more impactful to start a family with an afflicted male or a heterozygous female for an X-linked recessive trait. That is enough information for our pedigrees for now. I hope this has been helpful. Be sure to answer the questions and have well drawn out pedigrees.